Now, organic chemistry is important because organic chemistry contains those carbons, and if you take a look at all of these molecules, carbohydrates, lipids, proteins, nucleic acids, these are what we call our 4 categories of macromolecules. Large molecules we build up from smaller functional groups, right? Carbohydrates are what we just mentioned. They are formed by monosaccharides, right? If you take a look at all of these organic chemistry and biochemicals in our body, what do they all have in common? Carbohydrates got a lot of carbons, a lot of hydrogens, lots of oxygens. Lipids, exact same atoms, carbons, hydrogens, oxygens, right? That's how we can convert one from the other. So if you eat a lot of carbohydrates, people think that if you eat a lot of carbohydrates but not fat, you don't gain weight. Kind of crazy. But what happens is there's a limit to how much we can store just simple sugar, right? There's a limit to how much we can store carbohydrates. If you go in excess of that limit, you eat too much, and now your stores of carbohydrates in your cells are used up. Well, what do you do with that extra carbohydrates? Turn it into fat. And again, there's almost no limit to how much fat we can produce and store. And the great news about fat is this. It has, especially the triglycerides in our body, it has no other function than to be storage form of our energy. Right? It allows us to just store energy for long periods of time. Proteins, also composed of what? Carbons, hydrogens, and oxygens. Now, depending on the amino acid, you might have more nitrogens, sometimes even iodine, right? But the base kind of skeletal structure of an amino acid is identical to carbohydrates and fat. Again, we have 8 essential amino acids. The other 12 we can make and we can convert one from the other. We can convert carbohydrates into it. It takes a lot of work and it takes a functional liver, but you can convert it. Nucleic acids, DNA, RNA, are made out of carbon, hydrogen, oxygen, and then a little bit of nitrogen and phosphorus. So they all have very basic skeletal carbon, hydrogen, oxygen, right, group right in the middle, stabilizing it. Let's talk about the first one, carbohydrates. Carbohydrates are going to be divided into monosaccharides and disaccharides. Monosaccharides, mono meaning one, right? Saccharides are types of sugars. And what you're going to see is that when we draw a monosaccharide, we can draw it 2 ways. We can draw it here, right? Kind of the straight form, glucose right here. Right? So here's a straight form of glucose. You can draw it this way, or we can draw it in its ring form. Usually the ring form makes it easier for us to make bigger molecules of glycogen, but these two are exactly the same. These two are exactly the same, right? Now, when you look at the ring form of sugar, each point, here's one point, here's another point, here's another point, here's another one, here's another one. Each point represents a carbon, right? So each point here, 1, 2, 3, 4, 5 carbons, and then the last one, 6. 6 carbons. How many carbons do we have here? 6, right? So the only difference is how they look. Chemically, they'll react the same way. If you look at, these are our 3 main type of monosaccharides. You don't need to know the structure, you need to know the names. We have 3 monosaccharides, fructose, glucose, galactose. Out of all those monosaccharides, we form larger polysaccharides. How many of you guys, when you guys were in high school, right, ate a lot of glucose or a lot of pasta a day or 2 before a big basketball game? a big wrestling match, right? Before a big football game. A couple days before, you'd have big pasta dinner, right? Now, we know that shouldn't happen as much because we kind of understand the basis of it. It's kind of flawed. When you have when you eat a lot of pasta, pasta contains starch. Starch is just basically glucose molecules bonded together. Very, very, very long chains of glucose bonded together. That's all starch is. So when we break it apart, we increase our blood glucose, and then what we want to do is take that extra glucose and then store it as human starch. So then we have energy. Human starch is glycogen. So glycogen is the animal form of starch, right? And what glycogen and starch means, it's long chains that are sometimes branched, meaning that, right, here's a branch point right here. You might have another branch point over here, allowing you to store a lot of glucose in a very short space, very small space. Long chains of glucose. So they're the same thing. The only difference is, where do we see it? We don't see glycogen in plants. Or, we don't see the glycogen in potatoes. Instead, we see starch, right? But it is basically the same material, glucose bonded with each other. When you eat a high pasta, or, you eat a lot of pasta, eat a lot of rice, what happens is that we have the ability to absorb the rice, absorb the glucose, because rice is just starch, right? Just long chains of glucose. We have enzymes that can just break it apart. As we break those long chains apart, we store each one. And now we're gonna make the animal form. We break the glucose apart, we absorb it, now we're gonna make glycogen. Glycogen then is our way of storing glucose. So if you eat too much starch though, you have too much glucose in your body. The weird thing is this, there's only two places in our body where you see glycogen. First place, skeletal muscles. That's why we want to do it before a big meet, because you can store glycogen in your skeletal muscles. So then you can break it apart when you really need that energy, and then as you break it apart, I just free up a glucose molecule, put it into the bloodstream, or put it into the muscle, and the muscle will contract quickly. You don't have to wait for more fuel from your bloodstream. You already have it in those muscles, right? Now, the other place you can have it is in the liver. The liver is your main storage area for glycogen. So when you eat a huge pasta dinner, you're eating lots of starch, you're absorbing individual molecules of glucose, and now we make the human form of starch. So then we can store that glucose for when we need it. The bad news is there's a limit to how much you can store, right? And that limit is usually exceeded when you eat like multiple bowls of pasta. So when you do that before a game, yeah, you're gonna, not turn it just to glycogen, you're gonna turn a lot of it into fat. So take a look at these. These are 3 monosaccharides. The weird thing is this, we can absorb each one, glucose, fructose, and galactose. So we break it apart in your GI tract, and then each one is going to be absorbed separately. The weird thing is, once we absorb it, it goes directly to the liver. The liver converts galactose. It converts it to glucose. It takes fructose and converts a lot of it to glucose. That's why you don't hear of a blood galactose count. You don't hear of a blood fructose count. You do hear of a blood glucose count, right? Even though we absorb each one of these, they get converted to that, both of them, right? Now, with these 3 monosaccharides, we can turn it into disaccharides, right? Here, this is what you usually see. We don't really see monosaccharides in nature, but you do see disaccharides. Sucrose. Sucrose is table sugar. It's also the sugar that's found in fruits that gives a fruit the sweetness. So when you're eating a fruit and it's very sweet, you're gonna have a lot of sucrose right here, right? It is sucrose, not fructose. So it's sucrose right here, right? The cool thing is this, that sucrose, we have enzymes in our GI tract that breaks it apart and makes this reaction go in reverse, right? As it goes in reverse, we can absorb each one separately. But when it's together, it won't be absorbed at all. So we need those enzymes. Now, we usually don't have a sucrase problem, right? With enzymes, usually we have like the name for it. Instead of saying lactose, the enzyme will be lactase, right? Sucrose, the enzyme will be sucrase. He'll break it apart. Most of the time, we don't have a sucrase problem. A lot of times we have this problem though, lactase problem, right? I know in my Asian family members have a problem with eating lots of milk and drinking lots of milk, eating lots of cheese. Why? With cheese, with milk, they all have lactose, right? When you have lactose, it is glucose and galactose bonded together. So imagine instead of fructose, it is this, galactose. These two sugars bonded together, right? Now, in some of us, we don't have enough of the enzyme to break it apart, lactase, right? Lactase, that we need that enzyme. If you don't have the enzyme and you eat cheese, eat ice cream, drink lots of milk, well, we don't have the enzyme, we can't break it apart. The lactose then will start to, stay in your GI tract. As it stays in your GI tract, it kind of has water that's drawn to it. And now you have water and sugar going through your GI tract. As it goes into your large intestines, we have bacterium there that uses the glucose and the galactose, uses that lactose, and it starts forming gas out of it. Now you have water and gas in your GI tract. Yep, that's a diarrhea that we see when people have lactose intolerance, right? Now, what do we give? Have you ever seen those pills, right? Well, those are artificial enzymes. You eat it before you have milk, you eat it before you have ice cream. What happens? Well, now you have the enzyme in your small intestines available, so when you eat the ice cream, those enzymes are replacing what you don't have. That lactase enzyme then will break it apart. So then most of the lactose will be split, it'll be absorbed, and now it's no longer in your GI tract, no longer producing diarrhea. And nobody wants to talk about diarrhea.
With the lactose milk, is there...
Lactase milk, yep. The ones that have lactase in it, they already have the enzyme already in it, right? Now, the weird thing is it doesn't taste different, right? And keep in mind that even though I can give lactase and eat ice cream afterwards, it's not foolproof, right? There will always be some lactose that doesn't get separated. So there's always that chance that you'll have a little bit more lactose still, right? And some people can still have mild diarrhea or stomach cramping as a result, right? So I always tell people just take more than you think, right? Because yeah, it might be expensive, but it's not fun being in the bathroom afterwards, right? Dreading and kind of regretting that you take so few. Right. Now there is another thing, and then we'll take a break here. In terms of glucose molecules, right? You guys know that cellulose right here, cellulose is going to be starch, right? Cellulose, we do not break down. We can break down starch, and as we break down starch, we can absorb the glucose molecule. But cellulose, we don't. What's the difference, right? In other words, this is going to sound gross. When you're eating potato, right? You eat a big potato. When you go number 2 the next day, does it look like a big potato? Gross, but doesn't, right? Because you absorb most of it. When you eat a salad, got lots of carrots. What happens the next day when you go number 2? God forbid, corn, right? Right? So yeah, it looks the same. So what happens is this, that kind of cellulose material, we can't break down and absorb. So it passes through the GI tract unhindered, right? Unabsorbed. So it looks the same because we can't break it down. So you think there's some big difference between the two then. That there's no way that we can easily absorb one and not the other. The weird thing is this. Starch, cellulose, they're all made from glucose. They're the same thing, the same monosaccharide. They're bonded with each other. The big difference is the bonds are different. The angle of the bonds are different. And that's the only difference. And again, keep in mind that each point here is a carbon. So what we see in a glycogen is that the bond here from one glucose molecule faces upwards. In starch, same glucose molecule, but the bond is downwards. Right? Our enzymes are so specific that our amylase, that's the enzyme that breaks apart starch in potatoes. It'll break that enzyme apart, it'll break that, the actual starch apart because the receptor, the enzyme receptor, can get in there and free each one. But when the angle is facing upwards, same bond, same glucose. Now the angle of the bond is slightly different. Can't break it apart, right? That angle of the bond doesn't allow our enzyme to get in there physically and bind to it. Think about how many times we have keys that look almost identical. So, right, you might have house keys for the back door and the front door. They look almost identical. And then you put it in and it doesn't work, right? Even though the ridges even look the same, right? Why? Is because there's a small difference in the way the lock and the key works, right? Same thing here. The receptor enzyme has actual physical binding sites. When the angle faces up, our alpha amylase can't break it apart, right? So it goes undigested, unbroken apart. So what you see is what you get out the other side. And the weird thing is, it's still glucose though. So some animals can do this, can break it apart. Cows, horses, goats, all right? They eat grass, they eat, all of the different types of glycogen and even the cellulose. And what happens is, if you've ever seen them, they're always chewing. They might not have been eating for hours, but they're still chewing. The reason why is it takes a lot of work. So they'll, eat a mouthful of grass, they'll chew it, they put it into a stomach, the first stomach, then you have a reaction in the first stomach, kind of breaking those bonds apart a little bit, and then they'll spit it out, and then they'll chew it again, right? And then they'll put it into their second stomach. And the thing is, if you've ever seen cow poop, most of us haven't, it's okay, right? It's not great, right? Or even, God forbid, elephant poop when you're at the zoo, right? What happens is, even after all that work, you can still see pieces of hay, pieces of, right, grass still coming out the other end because it takes so much work to actually break down the cellulose. But it's the same glucose molecule though. Isn't that crazy? All right, let's take a break. I'm gonna keep the door open and see if there's anybody still in the other room.